recording this. Okay, so in the last lecture, I think we spent most of the lecture to talk about this very interesting new concept or aspect of the solidification processes, which is for a stable planar growth, right? So for here, what we do is that we're zooming in into a very small region of the nucleus, and locally we can consider that the solid liquid interface is approximately a plane or a very flat object, right? And we consider that how what are the factors that determine the steady state propagation of the solid front, right? Because because in these processes we're interested in that the growth of the solid and convert or transfer more liquids into the solid, and we consider that how the steady state or stable growth velocity v or speed v is related to different factors, and based on the balance of the heat generated for converting a small region of liquid into the solid and the heat that is taken away through conduction, which again is kind of assumption in our setup. We derive the steady state velocity, which is basically given by these or related to these three important factors, right? We explain why they're related to the factors in this particular way, right? We rationale this particular expression and find out it's very reasonable. So that's what we, I think the main thing that we discussed in the last lecture. And then we move on and then begin to talk about a very interesting phenomena also in the solidification processes involving the instability of the planar interface, right? As we said before, or in the last lecture, it's quite counterintuitive to consider that the solidification front can be maintained as a planar object for all of the solidification processes, because if you look at what happens on the micro scale, on the atomic level, we have atoms adding to the solid surface, right? But there's no guarantee that you have exactly the same number of atoms adding to the same surface area, to the same area for all of this solid liquid interface. There always be the cases where in a certain region there are more atoms adding to, and there are other regions where the less atom adding to, right? So this will generate small bumpy regions on the interface, on the solid liquid interface or the solidification front. So what we're interested in is that this is inevitable. There's even if you do this very carefully, I don't think you can maintain this to be a flat surface. So so having these small bumpy areas growing on the surface, or at least forming on the surface, is inevitable. So what we're interested in is that under what condition, or or generally speaking, are these small bumpy thing are thermodynamically favorable or not favorable, so they will further grow or melt back to maintain a planar solidification front. This is what we're more interested in. And in the last lecture, I think without doing any mathematics, we already rationale that in general these small bumps will be favored and they will grow. Right? There are two reasons for that. Number one is because in our system, we're actually imposing a temperature gradient in the liquid, right? So as you move away from the solid liquid interface, you have a lower temperature in the liquid region. So if you have a small bump that intrude into the liquid, this means that the tip of the thing gonna feel a lower temperature. And a lower temperature is good, right? Because it's in general going to impose a larger degree of supercooling, which will favor growth. And the other reason why is that, as we showed before, based on this expression, right? We know that the velocity, the growth velocity is proportional to the temperature gradient. And when you form this small bumpy thing on the surface, this bumpy area going to squeeze the temperature gradient. So you have a larger temperature gradient at the tip of this bump. So this will also, indicates that you, at least for the tip region, you're going to have a larger growth velocity compared to the flat regions. So all of these two factors basically pointing to the same direction, that in general, if you have the small bump form, and in our particular system, it will probably grow. Okay, so this is what we discussed in the last lecture, right? So now we're gonna, work out the detailed mathematics to see how, what are the conditions, what is the, geometry involved, what are the thermodynamics involved in order for us to see really the growth of this thing. So that's the main topic for this lecture. But before we talk about that, let's revisit the concept of Gibbs-Thompson effect, because that's the key concept we're going to use a lot in today's discussion. Okay, so I think this is the the plots illustrating the Gibbs-Thompson effect, and I think this stage I'm assuming that we should be very familiar with this, but let me revisit this again. So the basic idea is the following, right? So this is we discussed the first time we discussed Gibbs-Thompson effect is the case that when we talk about this, finite size nucleus and the effect of curvature on thermodynamics, right? So we know that if you're looking at or compare infinitely large solid phase and infinitely large liquid phase, you're basically working with these two free energy curves, right? And this Tm, which is the theoretical melting temperature, which is corresponding to the case that both the liquid and the solid phase are infinitely large, so there will be no effects from the interface, right? So this is a Tm, which is the theoretical melting temperature. Okay, now, based on the theoretical melting temperature, we say that, okay, so if I want to quickly see solidification in the processes, I will impose a larger degree. I will impose a lower temperature to, for example, T star, right? So let's take water as an example, but this is very generic. So for water, we know that the melting temperature equals to 0 degrees Celsius, right? So now, say that I impose a lower temperature to the system, I decrease the temperature to -5 degrees Celsius, which is this one. Okay, so that's my T star. Okay, so in this case, I impose a 5 degree, okay, of delta T, right? So because my delta T is like 5 degrees lower than my Tm, so I basically induce a 5 degree of supercooling in the system. Okay, so this is my delta T in this case, or I call that delta T naught. Okay, equals 5. I didn't write the unit, but this 5 degrees Celsius. Okay, so that's basically the general setup. But if you look at this more carefully, okay, so we say that my delta T naught is 5 degree, okay, meaning that the supercooling is 5 degree Celsius. But this 5 degree is with respect to what? What system? This 5 degree of supercooling is with respect to the system which has a melting temperature of 0. Does this make sense to everyone? Right? So my current temperature I choose to be T star, which is -5 degrees Celsius, right? I say that, okay, for a system compared to a system, I induce a 5 degree supercooling. So this implies that the melting temperature for that system is 0. Right? So that's why I can have 5 degree of supercooling. So this means that, okay, when I say this T naught equals to 5 degrees Celsius, this means I'm referring to a infinitely large solid phase, right? Which has literally a very flat surface. So there's no effect of curvature. Only for that system, it can feel a supercooling of 5 degree for this particular setup. Does that make sense to everyone? Okay. Okay, I'm assuming this is clear, right? So now let's look at the another case where I'm looking at this particular nucleus, right? I know that we work out this together. We know that this is the nucleus that we would produce, or the nucleus of the critical size, right? Corresponding to this delta T. Okay, so how do you get this nucleus? If you do the overall energy plot, you're going to see something like that, right? So this is my delta G. And we know the reason why you see the initial increase is because the surface energy dominant and then the volume term dominant. So this is going to give us the R star. And from this free energy analysis, we know that R star is the critical radius, for the system. So for any radius smaller than this, it won't grow. And for any radius larger than this, it will grow, right? So this is a critical radius. Okay, so now my question for you is that now if we're not looking at the infinitely large solid, but looking at this particular radius of R star, okay, for which it use all of the free energy advantages due to this delta T, to overcome its interface energy. Okay, this is basically the meaning for the critical, right? Is the critical nucleus is because that it use all of the free energy reduction to overcome the barrier for the surface energy increase. So that's make it to be critical, right? So for this nucleus, what is the effective supercooling it feels? Okay, remember the supercooling is basically the melting temperature minus the current temperature you have. Okay, that's the supercooling, right? Now for this R star, what is the supercooling it feels? What is the effective melting temperature for this R star?
T star.
The effective melting temperature is T star, right? It's minus 5 degrees Celsius because that's the definition of critical, right? So at this point, it has this particle, including the surface, right, has exactly the same free energy as the liquid at this temperature, which is illustrated here, right? So because you have this surface term, it basically lifts up this free energy of your particle. So this is the intersection of the liquid and solid free energy for that particle. And you see that the physical meaning of this point is exactly the physical meaning of this point, which is effectively the melting temperature for this particle of finite size of this radius r star, right? So this means that for T star, okay, the particle is just critically stable, which means that T star is the melting temperature for this particle. Does this making sense to everyone? Does this make sense? Yeah, we discussed this many times. Okay, I hope that at this point this is very clear, right? So now if R star, associated with the effective melting temperature, which is T star, and I decrease, so basically I set the system to be at this temperature T star. What is the the effective supercooling this particle feel? Does that particle feel any supercooling?
No.
No, right? Because this particle needs, so basically this means that the melting temperature for this particle is minus 5 degree. I set my temperature of the system to be minus 5 degree. So the system's temperature is exactly the same as the melting temperature for this particle. So this particle feels no supercooling, right? It's just critically stable, but it feels no supercooling. Does this make sense to everyone? I just want to make sure. Okay, so now, okay, if this is clear, let's look at another guy, which is this R2. Okay, and we know, as a matter of fact, R2 is probably here, right? So it's larger than R star, so we know from this free energy analysis it will grow, right? This is what we know as a matter of fact. And also what we know from the exam, from the homework, that we can effectively compute the melting temperature for this particle, T2, right? And we went through this in the solution of the exam, so at this stage it should be quite clear. And also we know that T2, based on this Gibbs-Thompson effect calculation, is greater than T star. Okay, so let's assign a number for this. Let's say T2 equals minus 2 degrees Celsius. Okay, it's higher than T star, right? Because your T star is minus 5 degrees Celsius. So T2 is higher than T star. Okay, this is making sense, right? Now, if I'm asking you then, does this R2 particle feel a supercooling?
Yeah.
Yes, right? Because my current temperature is much lower than what is need, okay? Or it's lower than its melting temperature, so it feels a supercooling, right? That makes sense to everyone? Okay, now what is the supercooling for this guy? What is the effective supercooling for this particle? We call this delta T2. I give you the numbers, so it's much easier to compute. What is the effective supercooling for this guy? Again, how to 3, right? How to compute the supercooling? Okay, so T2 is the melting temperature, right? I take the melting temperature and I minus the current temperature of my system, right? This is my supercooling, right? The degree of supercooling. Now my melting temperature is what? It's minus 2, right? And this T star is minus 5, and I have minus sign here, so it's plus 5. So I have a 3 degree of supercooling. Does this make sense to everyone? Okay, so basically this is the effect, the Gibbs-Thompson effect in terms of the supercooling. Okay, this is what we're getting now. I'm using this numerical example, but we're going to show something more generic. But this is what we're trying to illustrate. So you see that the Gibbs-Thompson effect in the previous lectures or in the previous context. What we're interested in is how the Gibbs-Thompson effect affect, right? How this Gibbs-Thompson thing affect the effective melting temperature like T star, T2, or T1, these type of things. So we can determine whether the particle going to grow or going to stay the same or going to shrink, right? So we're going to get the effective melting temperature based on the Gibbs-Thompson consideration. But now we're moving one step forward. Okay, not only we want to get effective melting temperature, we also want to get what is the effective supercooling felt by each particle with different radius. Okay, and that is connected to the melting temperature through this very simple relation. So that's basically what I'm trying to illustrate here. I think through this example, it should be quite clear. But the point is that you see, although you impose a initial supercooling, this delta T naught with respect to an infinitely large solid phase, but because if your particle has certain finite radius, right, the supercooling the particle fill will only be smaller. It's only a small portion in general of this T star naught. I'm sorry, delta T naught, right? Like this delta T2 is a small portion. It's a portion of delta T naught. It's not full delta T naught because it has a finite curvature. It has a radius that is not infinity. So this is generally true, right? So and we're trying to get, because the degree of supercooling is the driving force for that particle, it's determining a lot of things. So we need to find a general expression that allow us to, connect this effective degree of supercooling to the particle size, right? This is what we're looking for. Okay, and I'm illustrating this through this numerical example. Now I'm going to do a more rigorous derivation. So now based on our previous example, you see if this is my particle, this is T2, right? And then this is the supercooling fields. So it's only a portion of the full delta T, right? It's quite clear. But now what is the mathematical relation between these things? Okay, now we're going to do some derivation, but based on our discussion, I think the derivation would be straightforward. Okay, so let me do this. Yeah, so the idea is first, we know that this critical radius, right, use all of the degree of supercooling to overcome the interfacial energy, and R star is related to delta T, which is the supercooling induced through this relation, right? And then basically we can derive the expression for delta T in terms of the the critical radius of the particle, which is just to move this to here and this here. Is very straightforward. And then we can compute the T star, right? And this is exactly the same as we did in the exam, which is Tm minus delta T. This is basically going to give T star, which is given by this expression. And you see it's related to the, 1 over R star here. Okay. Now, for the same reason, why we're interested in T star, because we want to compute this portion, right? So now let's look at, suppose that we need a supercooling. Okay, so suppose that we know the radius for this one is R2, okay, and we know what is the critical supercooling, right? The critical supercooling to stabilize this particle, which is given by the same expression you have here, okay? And then we can compute this effective melting temperature for this particle, which is given by this, right? I think this is the same thing that we derived in the exam. So T2 is basically, let me illustrate this for you. This guy, right? T2 is this line corresponds to, Tm is the melting temperature. So my delta T2 is basically this part, okay? This is a supercooling with respect to the theoretical melting temperatures to stable my radius R2. Okay, so if I take this Tm and minus this part, I get T2, which is this line. This is my T2, right? But we're not looking for T2. We're looking for this part, the effective supercooling felt by the particle. Hopefully I'm not messing up of the symbols. Yeah, so this effective supercooling, I use delta T effective for the particle equals to T2. Okay, what is T2? T2 is this line, right? This is T2. And T2 minus T star. So basically, you're getting this part, right? This is my effective supercooling for my particle R2. If you plug in the numbers, if you say, my R star, T star is -5, and this T2 is -2, you plug in these numbers, you're going to get -3. This is exactly as what we did before, but now we're just making it more general. Okay, so having that, if you just plug in, you have already T star, and you have already T2, you already derive these two expressions in terms of, generic terms, just intrinsic to the system and to the geometry of these particles. You just plug in these two expressions here, Okay, and I think you should get a very elegant expression. So to do that, you just plug in this two in this equation. Okay, um, did I have that for you? Yeah, but I think I omitted probably one step, but basically it's very straightforward. Just to plug this back into the equation, and you can easily compute that. Okay, so let me show here. Okay, so here's a different way of computing that, which is very basically the same. So I'm now illustrating this idea. I think it's clear that we have illustrated the idea. Now, how we can apply this to the instability analysis. So as we said before, we're interested in the gross velocity at the tip of this small bump, right? So imagine that we have a huge solid back here, which we didn't show. Okay, you imagine this is a flat surface here with some other bumpy thing, but this is the most important small bump here. We're interested in analyzing what is the gross velocity at the tip of the small bump, and want to compare this to the rest of the the flat solidification front, and this will allow us to determine whether this guy is going to grow or not, right? And we also assume that for sufficiently small region at the tip, you can always approximate it as a part of a circle and associate it with a curvature or a radius with this particular curvature. So that's our setup. Okay. So now how we are going to apply the Gibbs-Thompson effect to the system? Okay. So here there are a number of important. Let me pull this down here. Let me. Okay. So here there's a number of important temperatures that I want to highlight. The first one is the melting temperature. Okay, so this is in the previous slides we showed the melting temperature is just a reference, right? And this T infinity is the temperature I impose into the system. Okay, in our previous example we use this T star. Okay, but here is the same thing. We just impose a temperature in the system, and far away from the tip, it basically it's a stable temperature. We call this T infinity, but that's the same thing as T star. Okay, so the difference between the melting temperature and the temperature you impose in the system defines the theoretical supercooling for the system. Now I call this delta T naught. Okay, so this is basically the same thing as we discussed, but using a different illustration. Okay, so again, Tm is the melting temperature. T infinity is the temperature I impose in the system. So the difference between these two gives you the theoretical degree of supercooling that we impose in the system. Okay, this makes sense, right? And then another important factor or temperature is what I call Ti. Okay, so what this temperature is in our previous language is going to be our T2. Okay, so this means that I have a particle with a particular radius r. Okay, in our case we have R2, right? So then this particle is going to have effective melting temperature. Okay, so this Ti, I represents the interface. It's the effective melting temperature at the tip of this interface. Now, why this temperature is lower than the Tm? Because the interface has a finite curvature, right? So because it has a curvature, so it kind of increases the interface compared to the full flat thing. So it used some portion of the degree of supercooling to overcome the surface energy, and that portion used due to the radius is given by delta R. Okay, so this part is what we call delta T2, right? This is what has been used to overcome the surface energy in our previous slides. Okay, so now you see that it's very easy to compute this one. The delta TR simply equals to the same expression we derived before, right? This is how we get the relation between delta T and R star. But now if we think that R star is just my current radius R, and we can easily derive the relation between delta R and R using the Gibbs-Thompson consideration. Okay, so and again, this is the degree of supercooling that used in order to overcome the interface energy for this finite radius. Okay, now we also know that if you impose this delta T naught, which is the theoretical supercooling, you can also find an R star, which use all the supercooling to overcome its surface energy, right? And this is an expression that we've seen many times. Okay, this is how delta T naught is related to R star, right? And now when we have these two numbers, when we have two of those expressions, it's very easy to compute what is the effective supercooling, right? We call this effective supercooling felt by this interface. We call this delta C, right? And from this relation, it's very easy to see that delta C simply equals to delta naught minus delta R. Okay, and from the graph, you see, if Ti is my melting temperature, which is the temperature of this tip right now, and far away from this tip, we have T infinity. So this is the supercooling it feels, right? So it looks, if we want to assign numbers, we call T infinity equals to -5, T melting temperature equals to 0, and my interface equals to -5, -2. So I have a supercooling of 3. Okay, again, this is exactly the same thing that we analyzed before using numbers, but now we want to express this in a more generic term, and more importantly, in terms of the critical radius. Okay, so that's the relation and how you correspond to that, right? I think it's quite clear. This is the interface temperature. This is the temperature far away from the interface, and the supercooling is very easily computed as delta naught minus delta R. Okay, so with that, and we can easily move on to compute what is delta R, and if we again, if we combine these together, we want to get rid of these material specific quantities like gamma and LV. It's very easy to show using this two relation that delta R simply equals to delta naught times this factor R star over R. Okay, so because R is always an R star, right, in our setup, so this delta R is only a portion of delta naught. And if we have this relation, it's very straightforward that we can compute the effective supercooling for this tip, okay, which is delta C, and this equals to delta naught minus delta R. And if we express delta R as this expression, now we can easily show that my delta C, which is the effective supercooling felt by this finite radius, the tip of finite radius is only a portion of the theoretical supercooling imposed in the system, and the portion is the factor to give that portion is 1 minus R star over R. Okay, so again, because R star is always smaller than R, so we know this factor is always smaller than 1. Okay, and because the smallest R you can have for the system is R star, so this factor is between 0 and 1. Does this make sense to everyone? Okay, now we can check this relation to see whether it makes sense or not, right? So now we can take the two limits. Let's first take the limit that when R goes to infinity. So let's take this limit because R star is fixed, right? Once you fix delta T naught, you have this guy fixed. So there's nothing that we can play with these two things, but we can definitely play with R, right? If we set R is infinity, what do you get for the effective supercooling? Just look at this expression.
Delta T naught.
So when R goes to infinity, this factor here is 0, right? The second part of in the parenthesis is 0. So you get delta T naught. Does this make sense physically? What is the meaning of R goes to infinity?
It's the bulk.
It's the bulk. It's going back to the flat interface, right? It's going back to the flat solidification front because your curvature is 0, right? The radius is infinity, so it's a flat interface, and you're going back to the bulk solid phase, and you feel all of the supercooling. That makes sense to everyone? Okay. So now, what is the other limit? If we take the smallest value for the R can take is R star, right? Now, what is the factor if you let R equals to R star? What is this whole factor?
0.
It's 0, right? So what does this mean physically? This means that if I have a particle or have a curvature, the curvature of the tip or the radius of the tip equals to critical radius for this delta naught, I do not feel any supercooling at all because I use all of the supercooling to overcome the interfacial energy, right? Does that make sense to everyone? Okay, so for
Yeah, I have one question, please.
Sure. Go ahead.
As you say, like when you say the radius goes to infinity, and that equals zero. It's like we're moving from like a microscopic perspective to macroscopic macroscopic perspective, right?
Not really. So when the R goes to, in here, we're still having this curvature, but you can imagine that this thing gonna become more and more like this, right? So this is the meaning of R goes to infinity. So if eventually you're going to a flat surface, but I don't think this changed the length scale. It's just the local curvature. You're still looking at a small region, but the curvature, because R is not the size of the thing, it's only the locally, it indicates the curvature, right? It only means that you're still looking at this local region, but the curvature is 0, or the radius of that thing is infinity, but you're still looking at this, for example, this small region, like, but its curvature is very large. Does that make sense?
Thank you. Yeah, thank you.
Yeah, good question. Okay, so yeah, that's that. Okay, so yeah, I think this is clear. But yeah, so this is a very simple relation that we are after. But I think it's worth the effort to go through all these details so that we can appreciate the meaning of this and how we get this. Okay, good. So now let's go back to what we're trying to do, right? Because this is just an intermediate step that we have to do in order to figure out this guy, right? Because we're interested in knowing what is the curvature, what is the velocity of this tip, right? But now why we have to go through all the trouble to compute delta TC, because we need to use this delta TC to compute this guy, right? Because if you look at this expression, okay, you cannot change K, you cannot change LV once the material is fixed, right? But the temperature gradient, is definitely something that is related to the geometry of the sky, right? And also is intrinsically, to the degree of supercooling it fills, right? Because the reason why is that if we are assuming that the system, for example, this curvature of the tip is right here, we're always assuming that for the steady state or for any growth, if you look at the condition to derive this equation, right? We're assuming that in the solid phase, the system is kept at a constant temperature that equals to its melting temperature, right? And this is the condition that we derive this whole expression. And then in the liquid, we can have a temperature gradient of arbitrary form. But within the solid, we're assuming that somehow we were able to at least locally keep the solid at its melting temperature or effective melting temperature. Okay, so now this condition basically means that at this tip right here, at the solidification front of the tip, the temperature is actually Ti, right? And the system's temperature is T infinity. So, this difference, which is given by Tc, which is just the supercooling that felt by the system, we compute. Okay, now why we need that? Because once we have this Tc, del Tc here, and we can estimate, I'm sorry, this is bad drawing. We can estimate what is the effective temperature gradient, okay, right in front of the tip here, and use that to estimate our velocity. Okay, so that's why we're using this. Okay, now we're moving forward away from this slide and to talk about how we're gonna plug in or use this, conclusion from the Gibbs-Thompson effect and combining this generic velocity of growth to get some very interesting analysis. Okay, so as we said before, if you want to use this expression to estimate the velocity, right, the key thing that we need to do is to estimate the temperature gradient. Now, because we know that it's always going to be a negative gradient or a slope, right? So, but the velocity is positive, so I'm just taking the absolute value for this and take away the minus sign because I think it's easy for the computation, but it is the same thing, okay? The key thing is to estimate the temperature gradient, right? So I think there should be a absolute sign here. And the idea here is that we're approximating, so the actual profile of this is a little bit more complicated, which we will derive later, probably in the next couple of lectures. But for now, we're just using a very a kind of common conclusion observation from diffusive transport that if this non-uniform temperature field is imposed by a finite size of this particular tip, okay, and we're interested in the temperature gradient, right? So the gradient is basically that you take the difference of the temperature and divide a certain distance over which the temperature decay from this Ti to T infinity. right? And we already know the difference between Ti and T infinity, which we computed as delta Tc. So what is the length scale or characteristic distance that you should use, to compute this or estimate this gradient? And again, from the rigorous solution of diffusion equation, that distance, a very good distance to use is simply the radius of this tip, which is r. Okay, so which means that the distance over which the temperature decrease away from, as you move away from the tip, is roughly the distance of the radius of the tip. So for any finite, for any tip with a finite radius, it only gonna affect the finite region of the temperature field, and that is a kind of a very well-known observation in the diffusion, in the solution of the heat transport of the diffusion equation like this. But we'll just directly use that conclusion here. So basically we take approximate of the temperature gradient, which is delta Tc, again, which is this part, divided by a characteristic length over which the temperature decay. And that length is taken to be the radius of the tip, okay? So, and that is dt over dx, okay? And if we consider that and plug this back into this equation, okay, what we have is that, the delta Tc, as we computed before, okay, is delta T naught times 1 minus R star over R, right? But because we're using the curvature, we're using the temperature gradient, and there's another R factor come in as the denominator. Okay, so if you plug in the previous expression we have for delta Tc in here and use this approximation for temperature gradient, we basically obtain the temperature gradient is related to the theoretical supercooling, but it's non-trivially dependent on the radius of the tip. Okay, there's 2R here. Okay, so it's not very simple. It's a non-trivially dependence on the radius. Okay, so that's what we have. But nonetheless, once we have this approximation of temperature gradient, we can directly plug this back into the equation for the velocity. Okay, and so we have the R-dependent growth speed. Okay, which is this guy. Okay. So again, this I use this approximate is because this here is approximate. So rigorous speaking, there might be some constant related to the geometry of the tip or due to the geometrical correction for this R, but it's a very good approximation for the purpose we're for our class. We're not looking for a rigorous expression for this. We're just interested in general how the growth speeds depend on the radius of the tip, and that give us the correct scaling. Okay, again, this first two terms is just inherent from here, and then this whole thing back here is the approximation for the temperature gradient. Okay, so that's the expression we have for here. And I say this is non-trivial because, if you look at this relation, okay, it's a non-monotonic, right, relation or it's non-monotonic function of R, because this 1 over R is a monotonic decreasing, but this 1 minus R star over R is monotonic increasing. Right, so you have a decreasing function times the increasing function of both R. So we know this is non-monotonic, and this implies you have a local maximum or minimum of velocity, right? So depending on what is the radius you have, the gross velocity is quite different. And there is if the radius is too large, it's not good. If the radius is too small, it's not good. So there is a delicate balance that gives you the best gross velocity. Okay, that is what we're looking for. Okay, so if we look at this expression more closely, okay, so the first we see that, if the radius is too large, it's not good, right? Can we see this? So if the radius is very large, we definitely have very good supercooling, okay? This gives us a large driving force, but we have a very small temperature gradient in this case, right? So overall, if R goes to infinity, I don't have any growth anymore in this case, because basically I'm considering the temperature gradient is solely imposed by the curvature, right? So too large R is not good, and too small R is also not good, because when R is very small, clearly you have a larger temperature gradient, right? But also, you have a much smaller supercooling, so this will also not give you a very good growth because the driving force is too small, right? So this means that you need to have a delicate balance, and if we do a rigorous analysis to find out what is the local maximum for this gross velocity, okay, with respect to the radius. How would you do that? How would you find out what is going to be a maximum, gross velocity and the corresponding critical radius for that maximum growth velocity.
Take the derivative.
Yeah, take the derivative of this guy. But basically I'm showing the a ref plot for this guy, right? When r goes to, this is r star, this is not r0, you don't have any velocity. When r goes to infinity, you don't have any velocity, but you have this critical radius of the tip that give you the maximum growth velocity. And to get this, you just take a derivative of this v with respect to r, and it's very easy that you have a quadratic, I think, or even simpler thing, to solve. And you can easily find out that this maximum growth speed is achieved with r equals 2 times r star. Okay, so this is a very, I wouldn't go through the mathematics. I think I leave the homework problem for you to derive this. But once you have this expression, just taking the derivative, and it's very straightforward to get this result. Okay, so I'm leaving that for you, but it's very straightforward to do. Yes.
This graph is velocity versus radius, right?
Yes, I'm sorry, I should make it clear. Yes, it's the velocity versus radius. This is r, and I think we're starting from r star. This is origin is r star. It's not 0. And then this thing is 2 times r star. And this is vr. Yeah, thank you for that. Yes, so that's that. So this is the maximum velocity. So what does this mean? Okay, this is interesting, right? So if you're looking at a single, we just look at one single bump, right? We know that, okay, it's this, you have different bumps, and whatever the bump has 2 times the critical radius is going to grow the fastest, right? But in reality, what you actually see is that in our analysis, we are assuming that there only a single bump exists on this flat interface, right? But this is generally not true. The reality is that when after you allow the particle to you allow the initial nucleus to grow, the surface is gonna transform into a kind of a vivid thing like this. You're never gonna have only a single nucleus, a single bumpy area. Is that the whole thing is composed of many bumpy area with different radius, everywhere. Okay, because the fluctuations is occurring everywhere, so it's basically makes the interface very rough. You have regions with large curvature, have regions of small curvature, right? So usually we call this the perturbation, right? And the size of this, which is the radius r. So basically we can say, the perturbation have some, characteristic length. We call this lambda. Sometimes, in other, papers or literature, you basically see people call this wavelength for the perturbation, but basically that's the same thing as r. Okay, the most simple relation between lambda and r is lambda equals 2r, in an assumption. But basically they're the same thing, characterizing the size of the tip. But if you look at many of these perturbations, all piped up in the solidification front, it looks like it's a wave, right? So you have a perturbation of a certain wavelength. And this analysis tells us that not all of these perturbations going to grow, right? You have a lot of bumpy small things, on the interface, but not all of them going to grow. Not all of them gonna grow at the same speed, right? So only the one have roughly twice of the size of the critical nucleus going to grow at a much faster speed than all the other ones. Very large bumps wouldn't grow, very small bumps wouldn't grow, fast enough. But the bumps have right size going to grow much faster than all the others. Now this implies a selection mechanism, right? So what do I mean by selection? So initially I have many of these bumps, right? They are large, they're small, they're different sizes, but only the ones that have roughly the twice of the critical radius that has been selected to grow much faster, and they're going to overcome and dominate in the system. Does that make sense to everyone? So like this one is not going to grow fast because it's too large. These two are not going to grow very fast because they're too small, right? And only a tip or a bump of roughly this size, which is 2 times the critical size of the nucleus, going to grow fastest. It's going to overcome all of the other bumps and intrude very fast like this. Okay, so we call this a wavelength selection processes. Okay, now what is the consequence of that? Okay, the consequence of this wavelength selection, in particular our analysis of the most favorable size of the tip, going to lead to a very interesting pattern for, yeah, this is velocity. If you just plug in r equals to r star, you get this velocity. Again, it's very straightforward. Something like that. Okay, so this is going to cause the typical dendritic growth, and it give you a kind of interesting selection of the dendrite curvature. So here I illustrate the first stages of dendritic growth. Initially you start with a very small nucleus. You can remain to be kind of a spherical for some stages, but as long as the nucleus is large enough, locally you can make things like a flat. It begins to develop a curvature, select the critical size and select a wavelength to grow like this. Okay, but when basically when this thing grows, you see that the typical size does not quite change. Let me highlight that for you. You see this local curvature, this length scale is roughly the same of this length scale, right? But as this thing further grow and grow, you see that on this particular dendrite, which is selected by, the width of the thing is roughly speaking twice of the critical radius, something like that, right? But as this thing grows, you see this part effectively become like a flat surface, right? And this part effectively like become a flat interface. So they're gonna, you will see some developments of a secondary bump from here and here. Okay, I'm sorry, this is not a good drawing, but basically you can see, right? And then it begins to grow. Roughly, the secondary thing begins to grow and select the same wavelength, select the same size or width of this. And then as this further grows, you begin to develop the ternary. So eventually this is going to allow you to grow into a very complex fractal object in 3 dimensions that is quite characteristic of all of these, the initial, solid stuff formed during the solidification processes. Okay, so this animation, this is from a simulation for solidification processes for which the free energy has a 6-fold symmetry. Okay, it's a little bit different than what we described before. In our analysis, we are always assuming that you have a perfect spherical symmetry you start with, so you can start with a circle, right, in your system. But in most cases, the free energy are not quite isotropic. They have certain symmetry, and in this case, we have a 6-fold symmetry, which is similar to the one you're seeing the snowflake, and you see that the growth of dendritic and secondary dendrites, right, in this way. So if you see that overall the tip is the same, it generates the tip, but you see the tip is roughly remain to be the same size of 2 times r star, and then you have the secondary thing, and the tip of the secondary thing also have roughly the same size. Okay, so this is a kind of interesting consequence of the wavelength selection. Now, one interesting thing is that because you have this important geometrical characteristic kind of, recorded into the system, right? Because you didn't know what is the temperature that you impose the system. You didn't know what is the condition if you see a snowflake. But after you see a snowflake, suppose you can do some measure, right? You can actually measure what is the critical radius for the tip, okay? Because you know the most favorable length or the length scale is 2 times the critical radius. And then, from that, you can basically get what is the critical radius from this geometrical imprint, right? And then you also know the relation from the critical radius to the theoretical supercooling. So this basically tells you that all of the, very cool snowflake or all of the solidification, small solid pattern that you see here has imprints of the thermodynamics, okay, you impose, or the temperature imposed to induce solidification. And this is through the Gibbs-Thompson effect. Okay, so this is a very cool thing that I just want to quickly mention. Okay, so with that, I think that's all I want to tell you for the growth of the solidification of pure system. Again, in this 2 lectures, I think have a good understanding of the concept of solidification in pure system, right? In this system, we just need to worry about how heat is taken away, because that's the only factor that possibly stops the solidification, right? When you convert some amount of liquid into the solid, it generates heat, right? And the heat has to be taken away in order for the solidification to be, keep on going, right? And we talk about 2 scenarios for the propagation of the solidification front. The first scenario is that you have the solidification front to remain to be a flat object, and this is very straightforward, didn't have very about curvature. And the second thing is that you would assume that there's a small perturbation on the flat surface. You have a small bump formed and use Gibbs-Thompson effect. we can obtain some very interesting analysis on the growth velocity for this small bump and understand a very important phenomena we see in the solidification, which is the formation of the dendrites and wavelength selection. Okay, so that's basically a summary of this solidification in pure system. Yeah, I think you have a homework problem for this, but I think we're clear on this one. Any questions up to this before I switch gear to another interesting topic? Okay, so if not, let me switch gear. We still have about 20 minutes, so I think we can probably talk about another interesting thing. Okay. Okay, so yeah, because this is the solidification in the pure system, right? So why we talk about solidification in the pure system first, because is relatively easier, right? Because we don't have to, for those systems, when we talk about solidification and growth, we just need to worry about the free energy, isotropic free energy, and also we only need to worry about the heat, right? So because for pure system, you don't have any solutes diffusing around, right? And as we understand this system, and we're going to now move to a more complex system, which is alloy system. So as you can probably imagine, the key thing that determines solidification of alloy is not only the temperature, right? We have to impose the correct temperature to grow, but also there's one important thing involved in the growth or solidification of alloy, which is the redistribution of the solutes, right? If you still remember, because if you look at any phase diagram here, right? During the solidification processes, I have the equilibrium composition of the liquid and solid phase constantly changing. So we have to worry about, the diffusion of the solutes in both the solid phase and the liquid phase for the solidification of alloy. So this adds another level of complexity. So that's why we reserve this for a later topic. So we first look at the solidification of the pure system, which is very clean. You just need to worry about the heat flux. But now let's move on to talk about the alloy. Okay, so that's the logic. Again, before I describe all of the technical stuff, I will first, like just to revisit what is the concept of solidification in alloy, as we can see from the phase diagram. And then because of the complexity of the system, we have to restrict our analysis, especially in the context of this class, to a very simple one-dimensional system, which is the directional solidification of alloy bar. Because if you're looking at even a two-dimensional system, there's no way for us to analytically keep track of the diffusion of the solutes, as you can probably imagine, right? Because the diffusion, depends on the shape of the nucleus, and the nucleus is going to change shape over the processes. So there's no way for us to, analytically write down simple equations for that. So we restrict our analysis, especially in this class, to a one-dimensional system. But you can use exactly the same insights obtained here to analyze higher dimensional systems, which are typically analyzed using numerical simulations. But the idea is the same. Okay, so we look at this one-dimensional directional solidification of alloy bar, and this allows us to look at both equilibrium and different non-equilibrium cases for the solidification and obtain some very interesting and useful insights. And also another reason why we use this example is that this is the way how people make these alloy bar. Okay, so it's also engineering and industrial relevance. It's not just we make up this example. It's kind of a real example in industry, in real life. So we use this. Oh, anyway, so that's why we use this very simple example, one-dimensional example. And we're going to talk about three cases for the solidification. Okay, the first one is very simple, equilibrium solidification. And from this one, we're going to happily recover level rule, from a completely different context. And the second one is that, we have a different assumption of how diffusion going to work in liquid and solids. And we find out some very non-equilibrium, relations between the solutes in both phases. And finally, we talk about a more realistic case, and we'll show how these things work in the real life. And finally, we introduce another cool concept, which again is very a little bit complicated. We call it sophisticated. We call compositional supercooling, because now, if you think about instability, you not only need to worry about temperature, but also have to worry about composition. Okay, so this is very interesting, cool idea. Okay, so let's start our discussion. Okay, so now let's, when we move to the discussion of alloy, I think the first thing we'll refer to is a phase diagram, right? Because this basically collect all the information you want and you need in terms of the thermodynamics for and phase transformation for alloy system. Okay, and this is very familiar phase diagram. This is the Latin eutectic phase diagram. I hope we still remember this guy, right? I think in lecture, I can remember 4, probably we analyze, we construct phase diagram like this, right? From the free energy analysis. And then we say that we can analyze different composition line. And by looking at this line, we can recover a lot of information about, the phase transformation and predict the microstructure evolution, right? So for example, if I'm following this line A, right, I'm going to see, starting from the high temperature, you start with a pure liquid state, like this one, right? And then you can enter into the two-phase coexistence. You're going to have both liquid and solid. But during this processes, you can construct a timeline, and you can actually get at any temperature the equilibrium composition of liquid and solid phase. Okay. Now we're going to be more specific about equilibrium composition later, but we get equilibrium composition for these two phases. And as you cool the system at this temperature, okay, you have exactly the system completely transform into the solid, right? So you have this alpha phase, but if you further cool, you're going to get into this precipitation growth, okay? But in our classes, because for now, we're only talking about solidification, so we're not interested in these two stages, right? We're all interested in this particular stage. When it get into starting from a liquid, you cool the system, you get into a solid, a two-phase coexistence, and then you keep on lowering temperature and you complete the solidification. Because we're talking about solidification, so first look at this. And later we're going to discuss the precipitation growth in detail. That is a solid phase transformation, but that is a topic later. For now, we're going to look at this one. Okay, and then you can have different pathways for the transformation, right? For example, if you prepare the system at a eutectic point, right? If you cool the system and you just have a very nice phase transformation that directly take you from the liquid to the eutectic transformation. Let me clear all this, and I have a slide for you. So that is along path C, right? So this is the eutectic transformation. And this is, again, another pathway for the solidification. So we will devote quite a few lecture to understand what is the thermodynamics, what is the kinetics for this transformation as well. And as you can imagine, this eutectic transformation involves very interesting diffusion phenomena, right? To generate these, kind of laminar structures. And we're going to discuss that in detail later. Okay, so yeah, and one thing is that this is a eutectic transformation, and then the last one going to be along the path B. Okay, so you have a mixture of this two, so it's generate a very interesting phenomena, generate a very interesting microstructure, but because there's no new transformation mechanism involved here, right? Basically, just you have the solidification, nucleation, growth processes, and you have the eutectic processes. So those two we will separately discuss. So there's no mechanism adding to this very interesting pathway, so we will not talk about this pathway. So we'll talk about nucleation and growth in alloy. We'll talk about eutectic transformation in alloy, but we'll not talk about what happens along path B because it's simply a combination of these two. Okay, so that's basically the context for the next few lectures. Okay, any questions up to this point? If not, I'm going to introduce our setup for this problem. Okay, so again, I'm only now taking a portion of the phase diagram, right? If you go back to this one, okay, so I'm now only taking this portion, right? I'm basically taking this portion because I'm only interested in this, right? We're interested in that you start from a liquid and cool the system. I have the two-phase coexistence, and then the whole system become a solid. This is what I'm interested in. So I just zoom into that portion of the phase diagram. But in order to make our analysis simpler, I make a very important approximation. Okay. So the approximation is that in general, if you look at the phase diagram that we analyzed before, usually the solid, so this is a liquidus, right? And this is a solidus. Those are two lines on the phase diagram tells you that, are distinguish different phase regions. And in a real phase diagram, these two lines are typically curves, but most cases they're not curved too much, especially at low composition. Because you can imagine that, you know, we're looking at alloy with very low composition of X naught, probably 1% or 2%. You know, in that very small, you know, dilute region, we can approximate these two curves, you know, approximately, you know, consider these two curves as straight lines. Okay, so this is very important approximation that we're making. Okay, so if we're looking at, you know, for example, X naught is very small, you know, dilute solution, and we can approximate both the liquid disk and solid disk as straight lines. Okay, so this will make our analysis much more easier. Of course, if they're not straight lines, you can also do very similar analysis, but it will add some additional complication. But so let's assume they're straight lines. Okay, all the insights we get from this analysis, assuming they are straight lines, also applies to general cases. Just make our analysis much more easier. So what is then the consequence of these lines being straight line? Okay, so there's a very interesting consequence. Okay, so because if this is a straight line, right, and this is a straight line, so if I choose any different temperature, okay, when I construct the tie line, for example, this one, this T2, okay, this tie line, I can get XS and XL, right? And I can construct different tie line, for example, this T3, this T1, okay, I can get corresponding composition for the liquid and solid, okay? So for example, for here, I can get this XS1, and this is my X naught, which is XL1, right? And here I get my XS3, which means the composition of the solid phase at T3. And I get this XL3. Okay, so now what I do is that, you know, let's just choose an intermediate temperature like T2. I can take the ratio between the liquid and solid composition. Okay, so let me take the ratio. Okay, so basically I take the solid composition, and then which is this one. Like you compare, you can consider this is just a line segment, right? Because on the thing you see this is a triangle, and you have this geometrical relation. Okay, I take this line segment and take this ratio, and I take this line segment and divide by this line segment, which is XS over XL. So I get a ratio, right? Because these are two line segments. I can get a ratio. I call this ratio to be K. Okay. Now my question for you is that this is the ratio that I compute by looking at the XS and XL for this T2 temperature. Okay. Now, if I do the same calculation for the liquid and solid composition, so if I take XS3 over XL3 associated with T3, I can get a ratio. Okay, I call this ratio to be K3. Okay, and I can do the same thing for a ratio for T1, right? I can take the composition of the solid at T1 and divide the composition of the liquid at T1. I call this ratio K1. What is the relation between K1, K2, which is said to be K, and K3?
Aren't they all the same?
They're all the same, right? Does this make sense to everyone? Because if you look at the geometrical relation, see, these are the similar triangles, right? So basically, you know, you start from this point, and this line segment is one of the bottom edge for this triangle. And this line segment is the bottom edge of this larger triangle. And because these are two straight lines, so all these triangles are similar, so the ratios of these lines are exactly the same. Okay, so that is the convenience that we introduce by assuming that the liquid disk and solid disk are straight lines. Okay, by assuming that these liquid disk and solid disk are straight lines, this means that during the coexistence region, okay, as long as I'm in the coexistence region, it doesn't really matter what temperature you have. If you take the ratio between the solid composition over the liquid composition, you can basically get the same number. Okay, so this makes things much more convenient for us to do our analysis. So this relation holds true, and K is a constant for all of the temperature, okay, between T1 and T3. Okay, as long as you are in this two-phase coexistence region, if you get any temperature, you get the composition for the solid and liquid, you get the ratio, you know, you get the same number K. Okay, so that is one important setup. So keep this in mind. Okay, and also if we look at this number, is k going to be smaller than 1 or larger than 1? So k is a number between 1 and 0, right? At least based on our setup for the phase diagram. Okay, again, this is a very important observation that we're going to use later. Okay, so that is one important setup we introduce. Again, we use approximations and consider that the liquids and solids are straight lines. And the convenience thing or the consequence of this assumption is that it allows us to get a constant ratio between the composition between the solid and the liquid for the entire coexistence region. And that ratio is between 1 and 0. Okay, does this make sense to everyone? Okay, now if we think we understand this, okay, now let me ask you a few questions, which is basically testing how good we understand this assumption. So let me say that, okay, so this is our phase diagram, and I choose this composition to work with. Okay, I select this to be my composition for the alloy. Now, what is, say, I start with a very high temperature here. Say I call this TH or T naught, very high temperature, right? What is the phase at this temperature, and what is the composition of this phase? This will be the liquid region. This is the solid. This is the liquid-solid coexistence. So what phase or phases do we have here?
You only have the liquid phase.
Well, I have the liquid phase, and the composition is X naught, right? Because it's kind of a homogeneous phase. Okay, so now let's say what is the significance of this point at T1?
Solidification begins.
Yes, this is the point where solidification begins, right? So this means that, okay, if I'm at T1, I just decrease a little bit, I should be able to see some small solid form, right? So now how many phases do I have at this temperature, or a temperature a little lower than T1? How many phases do I have? We have two phases. We have liquid and solid, right? Because we're now in the two-phase coexistence region. What are the corresponding composition? How would you get the composition for the two phases?
You can use the lever rule.
You just construct a tie line, right? Because we're only interested in the composition. We're not asking for the phase fraction. So we just do a tie line, and we know that intersection of the liquid is going to give us the liquid composition, right? And the intersection with the solid is going to give us the solid composition. So now what is the liquid composition? Roughly speaking, what is the liquid composition at T1?
X naught,
X naught, right? What is the solid composition?
KX naught.
KX naught. Does this make sense? Because we already, we know X naught, we only know X naught, right? But also we define constant K, which characterizes the ratio between the solid composition and the liquid composition for all temperature between T1 and T3. So for now, if your liquid have X naught and the solid will have KX naught, this is going to be the initial composition for my solid phase. Does this make sense to everyone? Okay, so that's you see the convenience come into play, right? We can easily compute the composition of any temperature for the phases. Okay, so now let's cool the system. Okay, now before we cool the system, let me ask you. Okay, so now if for the system, let's consider we have a bar of alloy, right? So now first, the heat is taken away from this direction. This is my heat flux, right? So at T1, for example, I know that I'm going to convert a small amount of solid into the liquid into the solid. This is at T1. So now my question for you is that if I keep the system at this temperature, say a little bit lower than T1, will the solid phase further grow? This is my liquid, this is my solid. Suppose this is my solidification bar. If I only keep the temperature at T1, does the solid phase going to grow? If I have iced water, if I keep the water at 0 degrees Celsius, does the ice going to grow? No, right? Because this is the equilibrium temperature for this amount of solid and this amount of liquid, right? Now we have alloy, right? Alloy, for alloy, the solidification not occur at a single temperature, it's occur over a range, right? And at each temperature. So now what I do is if I lower the temperature to T2, what do I see? Well, I see the solid phase grows, right? Because based on the level rule, I know that now I have a little bit more solid, right? Because for here, basically I have a very tiny amount of solid, but now I have this amount of solid and this amount of liquid based on level rule, right? Does that make sense? So the solid phase grow, but now if I cool the system to T2 and then keep the temperature at T2, what's going to happen to the system? What's going to happen to the amount of solid and liquid phase? The amount of the phase is going to remain to be same, right? They're going to remain to be this forever because that's the equilibrium amount you computed from the level rule, right? So what does this mean? This means that for the alloy solidification, it's not sufficient that you just cool the system to a single temperature. If you want to impose an equilibrium growth of the solid phase, you have to slowly cool the system, but continuously cool the system from T1 all the way to T3. Does that make sense to everyone? So only through these processes you can induce an equilibrium or cause the equilibrium growth of the solid phase that propagate from the left end where you take the heat away all the way to the right hand, to the red end where the entire system transforms into the solid. Okay, so that's that. Again, we were going to revisit this concept back forth again. So it's totally fine if you still feel this is a little bit confusing at this stage. But the whole point is that if you want to impose equilibrium solidification in the alloy, you have to slowly, very slowly, but continuously lower the temperature. Okay. And now, so finally, let's say, okay, if we are reaching T3, what is the composition? How many phases do we have? Just a little bit above T3, how many phases do we have? We have two phases, right? We still have liquid and solid, but the liquid is very, very small. Probably is, squeezed to this end. We only have this small amount of liquid. All the others are solid, right? What are the composition? Roughly speaking, what is the composition of the solid? It's X naught, right? Based on the phase diagram. Okay, what is the composition of the liquid? If my XS equals to X naught, what is the composition of the liquid?
Naught by K.
It's X naught divided by K. Does this make sense to everyone? Okay, so again, we haven't said anything about these transformations. We just introduce this model phase diagram, right? And introduce a few consequences, very interesting observations about, what happens if we assume that the lines are, the solidus and liquidus are straight lines. Okay, so I think I'll stop here. This is the time, so I'll stop here. Let me see, I think I have some additional stuff to show you at this. Yes, basically the same thing, right? If we're assuming that the solidus and liquid are straight lines, the ratio is a constant over the entire coexistence region, and this will make our analysis much more easier. And we only examine a little bit of the consequence for this assumption. Okay. Yeah, so I think we already did that. Write down the composition of liquid and solid phase at the beginning and end of the solidification for the composition line X naught. I think we're clear about that. Okay, so I will stop here. Okay, I'll stop recording and